So section 3.1 deals with the three-dimensional shapes of molecules. How do we predict these three-dimensional shapes? So the molecule's properties are a consequence of the three-dimensional orientation of the atoms and electrons around a central atom. Here's the ball and stick model of ethanol. Just like we saw on the previous slide, here's a Lewis dot structure of ethanol that appears to be flat. But if we make a ball and stick model from a model kit, or look at this picture here, we can see that the molecule is certainly not flat, right? The oxygen has sort of a bent shape to it. Each carbon here, these large black spheres, have hydrogen poking out in three-dimensional orientation. And so when we talk about the orientation of electrons around the central atom, it's called the electron geometry. The orientation of atoms around the central atom is called the molecular shape. And these are not always the same, so they can be different. How do we visualize the 3D shapes of molecules? We can use the ball and stick model like we saw in the previous slide, and we'll use this in the book and also in the homework. Or occasionally we can use space filling models where we show exactly how much space that carbon and hydrogen is taking up in this molecule of methane. More commonly we'll use the Lewis structure of methane shown here, which doesn't specifically show the molecular shape, but with practice we can understand that this shape actually leads to a tetrahedral orientation shown here in this ball and stick model. So we're going to use what's called VSEPR theory, valence shell electron pair repulsion. And that uses Lewis dot information to identify the location of the electron. So now we see why it is so important to be able to draw a good Lewis dot structure. So you should have worked the Lewis structure lab before chapter 3. So if you haven't done that already, please go back and work on the Lewis structure lab and then continue on with our study of chapter 3 right here. And so once we draw a proper Lewis structure, we can look at the location of the electrons in order to predict where the atoms will be, and that gives the molecular shape. So we need to draw the proper Lewis dot structure, then we look at the electron geometry, and we use that information to predict the molecular shape. So VSEPR theory states that the charge of electrons causes the pairs of electrons to repel each other. So the groups of the valence electrons will adopt a geometry placing them as far apart from one another. So if there are only two groups, they will be placed as far apart from one another relative to the central atom, which is essentially on opposite sides of the atom, 180 degrees removed. And when we're discussing groups of valence electrons, a single bond, a double bond, a triple bond, and a lone pair are all considered one electron group. So even though the double bond has 4 electrons in it, the triple bond has 6 electrons in it, still considered one electron group. So that's the number of groups around the central atom that determine the characteristic shape that can form. So if we have 4 groups around our central atom, 4 electron groups, which is such as we have in methane here, we have 4 CH bonds, and those are considered electron groups. There are 4 of them. That leads to a tetrahedral molecular shape, or electronic shape. And that has 109 degrees between the HCH bond angle. So there's 109 degrees of angle here, and it adopts sort of a tetrahedral shape where these 3 lobes or groups are pointed down towards the floor or the table or the work surface, and this lobe is pointed directly up, straight vertical. If we have only 3 groups, that leads us to a trigonal planar molecular shape, and 2 groups of electrons leads us to a linear electron shape or electron geometry. So the first step, Lewis dot structure, determine how many groups of electrons we have. If there's 4, we have tetrahedral electron geometry, 3 trigonal planar electron geometry. Notice the bond angles on trigonal planar are 120 degrees angles. So we have essentially a triangle denoted by the 3 electron groups. If there are 2 groups of electrons in our Lewis dot structure, we have a linear electron geometry where the 2 groups are 180 degrees from each other. So then predicting the molecular shape, once we've established the electron geometry is either tetrahedral, trigonal planar, or linear, we can move on to the molecular shape. And there are 3 possible molecular shapes for the tetrahedral electron geometry. That could be tetrahedral molecular shape, trigonal pyramidal, or bent. There are 2 possible molecular shapes for the trigonal planar electron geometry, that is trigonal planar or bent. And if we have a linear electron geometry, we have to have linear molecular shape. So that's an easy one to distinguish. If it's linear electron geometry, it's also linear molecular shape. And then the bond angles in any of these three here that derive from tetrahedral molecular shape are all 109.5. The bond angles in the trigonal planar or the bent molecule are 120 degrees, and certainly the linear molecule has bond angles of 180. So some examples of molecular shape. The Lewis dot structure shows 4 groups of electrons, like methane here. That is a tetrahedral electron geometry. Each of these 4 groups resides in one of these 4 lobes shown in this drawing here. If we have 3 groups of electrons, BF3 is a good example of that. There are only 3 bonds to boron, so that gives us 3 groups of electrons. That's a trigonal planar electron geometry. The FBF bond angle is 120 degrees. And we've seen carbon dioxide before. There are only 2 groups of electrons in this molecule, the CO double bond on the left, CO double bond on the right. And that gives us a linear electron geometry. And again, 180 degrees is the bond angle. So in tetrahedral electron geometry, we have 3 possible molecular shapes, and that will depend on how many non-bonding electrons we have, how many lone pairs are present in the molecule. So if we have 4 bonding groups in tetrahedral electron geometry, obviously we have 0 non-bonding groups, and so that leads us to a tetrahedral molecular shape. 3 bonding groups and 1 lone pair, like NH3, will give us a trigonal pyramidal molecular shape. And if we have 2 bonding groups and 2 non-bonding groups, such as in water, that gives us a bent molecular shape. So the most common shape is tetrahedral geometry, both electronic and molecular geometry. Most biochemical molecules are based on the tetrahedron. And here we show a 3-dimensional drawing of methane, a tetrahedron electron geometry and tetrahedron molecular geometry. So it's important that you learn to draw these 3-dimensional drawings. So here we have the 4 CH bonds. These 2 CH bonds are in the plane of the screen right here. These 2 bonds are drawn such that this one with a dash projects away from you, back into the computer screen. And this bond here with the thick black wedge is drawn as though it were projecting out of the screen towards the viewer. And that's hopefully resembles this ball and stick model right here. So it's important that you learn to draw these 3-dimensional drawings here. So that was tetrahedral electron geometry. 4 electron groups, no lone pairs. If we move on to NH3, here's ammonia. The Lewis dot structure is shown here. It has 4 electron groups, 1, 2, 3 NH bonds, and this lone pair. So 4 electron groups, tetrahedral electron geometry. We draw that the same as the ball and stick model for methane, except that instead of an H bond up on top, we have just this lone pair occupying a lobe. But we still have 4 regions of electrons in this electron geometry here. So ammonia is a tetrahedral electron geometry. However, because one of those electron groups is a lone pair, when it comes to the molecular shape, we do not count that lone pair. So we sort of cover that up, or we don't even see it. And we see this molecular shape, which is called the trigonal pyramidal. 3 points on the ground. This is the point of the pyramid. So this is trigonal pyramidal. The lone pair disappears in the molecular shape to become trigonal pyramidal. Again, these bond angles are still 109.5 because it's derived from the tetrahedral electron geometry. So what if we have 2 lone pairs and 2 bonds like we do in water? So here is water. Oxygen is the central atom. It has 4 electron groups, so it has tetrahedral electron geometry. 2 bonding groups, the OH bonds, and 2 non-bonding groups, the lone pairs on oxygen. So here we see tetrahedral electron geometry. The 2 lone pairs occupy 2 lobes. Here are the 2 OH bonds. When we look at the molecular shape, however, we don't focus on these electrons. We sort of don't draw them in, and we're left with just the HOH in this angle. So we have a bent molecular shape. That's where we get the bent molecular shape from 2 bonding groups and 2 non-bonding pairs of electrons. So water is a bent molecular shape, and it has approximately 109.5 degrees as the bond angle. And so it starts with tetrahedral electron geometry, but because there are two non-bonding groups of electrons, we arrive at the bent molecular shape. And this is the shape of water. Okay, what if we have three groups of electrons on the central atom? Now we have two choices. We could have three bonding groups and zero non-bonding groups, and that of course leads to the trigonal planar molecular shape, just like the electronic shape. This is trigonal planar electron geometry. Or we could have two bonding groups and one non-bonding group, so one lone pair. And that would lead to a bent molecular shape. So for example, here is formaldehyde. Here's the Lewis structure of formaldehyde, a CO double bond, two CH bonds. So the central atom, carbon, has three bonding groups around it. This double bond counts as one bonding group, or one electron group. So the bond angles between HCO and HCH will be 120 degrees, just like the angle shown in this triangle here. And because there are no non-bonding groups, the molecular shape is also trigonal planar, shown here in the ball and stick model. So formaldehyde has three electron groups, also three atoms surrounding the central atom, and so it has a trigonal planar molecular shape. On the other hand, sulfur dioxide is actually a bent molecule. Here's the proper Lewis structure for sulfur dioxide. Notice that sulfur has an expanded octet. It shares four electrons with this left oxygen. It shares 4 electrons with the rightmost oxygen. And it has one lone pair on it. So it has a total of 10 electrons in its valence shell. If we count electron groups, 1 double bond, 2 double bonds, and a lone pair. It has 3 electron groups, so it's trigonal planar electron geometry. Notice we draw the lone pair as a lobe as part of that electron geometry. But then, as we did before, when we look at the molecular shape, we discount this lone pair, and we see just the bent molecular shape. That's where we get the bent molecular shape, starting with trigonal planar electron geometry. And this angle is, again, approximately 120 degrees, because it is derived from the trigonal planar electron geometry. Then we get to the linear molecule. If we have 2 bonding groups, here we have HCN, hydrogen cyanide. Carbon is the central atom. There's a triple bond to nitrogen that counts as 1 group. There's a single bond to H that counts as another group, giving us 2 bonding groups. There are no lone pairs or anything else on the carbon, so we have just 2 groups. That gives us a linear molecular shape. Here's the ball and stick model. 180-degree bond angle between H and N. And so a linear molecule can only have linear molecular shape. It can't have any other derivations of the linear electron geometry. So let's look at this Lewis dot structure for ozone here. And we may have to redraw it a little bit more clearly. So what is the electron geometry for this molecule? What is the molecular shape of the molecule, and what are the bond angles? So, first of all, the central atom here, oxygen, has 1, 2, 3 electron groups, right? 3 electron groups. What type of electronic geometry does that lead to? That's trigonal planar. So that's the electron geometry. So let's call it trigonal planar electron geometry. What is the molecular shape? Well, we have 1 lone pair. So that gives us 2 bonding groups. That leads to bent molecular geometry. And what are the bond angles? 120 degrees, because we started with trigonal planar. So a better way to draw this might be O like this. So we have the three electron groups arranged in the trigonal planar electron geometry. When looking at the molecular geometry, you only see the O portion of the molecule, not this lone pair. So it's a bent molecule. The next question, write the Lewis dot structure for hydrogen sulfide. So S, H, H. And then we know that sulfur is right here. It's in group 6A. So it has 6 valence electrons plus 1 electron from each hydrogen gives us a total of 8 electrons in the molecule. So we need to draw 4 more. I already have 4 in the bonds. I need to put 4 more on. And remember that hydrogen will never get a lone pair or a second bond. So we have these bonds, hydrogens are satisfied. The only place for the 4 remaining electrons to go is on the sulfur. So now, what is the electron geometry? Well, there are 4 electron groups, 4 groups, tetrahedral. What is the molecular shape? We have 2 non-bonding groups, right, and 2 bonding groups, and so that leads to a bent molecular shape. Bond angles are the same as tetrahedral, 109.5 degrees. So why is the molecule not linear? Well, these lone pairs take up spaces on that tetrahedron shape, right? So if we draw that, here's a lone pair, here's a lone pair, there's a wedge for the hydrogen, and there's a dash projecting that hydrogen back into the screen. We see that the lone pairs here occupy 2 points on the tetrahedron, but when we look at the molecular shape, we just see the HSH shape, and that clearly here is bent. Clicker question 3.1. What is the molecular geometry of carbon tetrachloride, CCl4? So if we want to draw, first we have to start with the proper Lewis structure of carbon tetrachloride. And I think I have space right here. So CCl4. Carbon, chlorine, 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 and then each chlorine should have 3 lone pairs on it. That is the proper Lewis structure. These lone pairs don't play a part in determining the molecular shape, but it's still good habit to get into having all of them on your molecule anytime you draw a Lewis structure. And so here we'd observe that there are 4 electron groups around that carbon, and there are 4 atoms surrounding the carbon. So we have 4 bonding groups, and that leads to tetrahedral molecular geometry, because there are no lone pairs. So the best answer here would be tetrahedral electron geometry, answer C. How about the shape of larger molecules, molecules that may have more than one central atom? They're going to follow similar rules, and a simple example is methanol, CH3OH. It's going to have 2 central atoms, C, which has these 4 bonds to it, and oxygen, which has 2 bonds and 2 lone pairs. The ball and stick model shows that the carbon, as we might have guessed, would have tetrahedral molecular shape. It has these 2 hydrogens are coming out of the plane, going back into the plane, in the plane of the page, and in the plane of the page. Whereas the oxygen has bent molecular shape because it has these 2 lone pairs that we don't draw in over here, the bent molecular shape. So we just observe any central atom, and it's possible a molecule may have dozens of central atoms. And in that case, we could describe the molecular shape of any or all of those central atoms using the same rules we've just discussed. So here's a molecule that has more than one central atom, but we want to know what is the molecular geometry of the central atom, central carbon, in acetone. Here's acetone, the central carbon is right here. What is the molecular geometry? So we've already drawn the Lewis structure. We can observe there are 3 groups of electrons surrounding that carbon. That leads us to trigonal planar electron geometry. The molecular geometry in this case will be the same. There are no lone pairs around this carbon. There are 3 atoms surrounding the carbon, and so it is also trigonal planar molecular geometry.